tables for maximum ampacity in 310.16 are not overridden by the temperature maximum of 40 degrees Celsius listed in the circuit breaker housing for a dedicated circuit. The temperature rating on the circuit breaker housing indicates the maximum ambient temperature that the circuit breaker is designed to operate in. This rating does not dictate or limit the ampacity of the conductors connected to that circuit breaker. Instead, the ampacity of a conductor is determined by several factors, primarily its size, the material it's made from, and the type of insulation it has. Table 310.16 in the National Electrical Code, or NEC, provides ampacity values for various conductor types under specific conditions. These conditions include the ambient temperature and the number of current-carrying conductors in a raceway or cable. In a scenario of a dedicated circuit designed to handle a 225 amp load, the conductors used must possess an ampacity of at least 225 amps. Consulting Table 310.16, a 4/0 copper THHN conductor is shown to have an ampacity of 260 amps under certain conditions, making it suitable for the 225 amp load requirement. However, the 40 degrees Celsius temperature rating present on the circuit breaker housing is a critical consideration. If the ambient temperature surrounding the circuit breaker exceeds 40 degrees Celsius, it could lead to premature tripping of the breaker. This happens because the breaker's internal components are designed to operate within a specific temperature range. Exceeding this range can affect the calibration and functionality of the breaker's trip mechanism. To mitigate the risk of nuisance tripping due to high ambient temperatures, it's advisable to use a circuit breaker with a high temperature rating that matches the expected operating conditions. In addition to selecting the correct conductor size based on ampacity and considering the circuit breaker's temperature rating, other factors must also be accounted for to ensure a safe and compliant electrical installation. These include voltage drop, dirting factors for multiple conductors in a raceway, and proper overcurrent protection. Firstly, voltage drop refers to the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can negatively impact the performance of electrical equipment and should be minimized by selecting conductors of adequate size. The NEC provides guidelines for calculating voltage drop and recommends limiting it to a certain percentage of the source voltage. Secondly, when multiple current-carrying conductors are installed in the same raceway or cable, their ampacity must be derated to account for the increased heat generated. This derating is necessary to prevent the conductors from overheating and potentially causing a fire hazard. The NEC provides derating factors in Table 310.15 cone that must be applied based on the number of current-carrying conductors. Thirdly, proper overcurrent protection is essential to protect conductors and equipment from damage due to overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. The size of the overcurrent protection device must be carefully selected to match the ampacity of the conductor it is protecting. The NEC specifies rules for selecting the appropriate size of overcurrent protection devices in Article 240. When selecting conductors for a specific application, it is essential to consider not only the ampacity requirements but also the environmental conditions in which the conductors will be installed. Factors such as ambient temperature, moisture, and exposure to chemicals can all affect the performance and lifespan of conductors. The NEC provides guidance on selecting conductors suitable for various environmental conditions in Article 310. For example, conductors installed in wet locations must be identified as suitable for wet locations. Conductors exposed to direct sunlight must be sunlight resistant, and conductors installed in corrosive environments must be resistant to corrosion. In addition to the factors mentioned above, it is also important to consider the type of load that the circuit will be serving. Different types of loads, such as motors, lighting, and heating equipment, have different current characteristics. Some loads, such as motors, draw a high inrush current when they start. This inrush current can be several times the normal operating current of the motor. When selecting conductors and overcurrent protection devices for motor circuits, it is essential to account for the inrush current. The NEC provides specific rules for sizing conductors and overcurrent protection devices for motor circuits in Article 430. Other loads, such as lighting and heating equipment, may have harmonic currents. Harmonic currents are currents that are not at the fundamental frequency of the power system, which is typically 60 Hz in the United States. Harmonic currents can cause overheating of conductors and equipment and can also interfere with the operation of other electronic devices. When selecting conductors and equipment for circuits with harmonic currents, it is essential to use equipment that is rated for harmonic currents. The NEC provides guidance on dealing with harmonic currents in Article 220. In summary, selecting the correct conductor size and type for a particular application involves considering a variety of factors, including the ampacity requirements, the environmental conditions, the type of load, and the presence of harmonic currents. It is essential to consult the NEC and other applicable standards to ensure that the installation is safe and compliant. The temperature rating of the circuit breaker is a critical consideration for ensuring the breaker operates reliably and safely within its intended environment. The 40°C rating signifies the maximum ambient temperature in which the circuit breaker can function without its performance being compromised. Ambient temperature refers to the temperature of the air surrounding the circuit breaker, not the temperature of the conductors or the equipment being powered by the circuit. When the ambient temperature exceeds the circuit breaker's rating, several potential issues can arise. Firstly, the breaker's trip characteristics may be affected. Circuit breakers are designed to trip or interrupt the flow of current when an overload or short circuit occurs. The tripping mechanism is calibrated to operate within a specific temperature range. When the ambient temperature exceeds the breaker's rating, the tripping mechanism may become less accurate, leading to premature tripping or failure to trip when required. Secondly, the breaker's internal components may be damaged by excessive heat. Circuit breakers contain various components such as contacts, insulation, and electronic components that are sensitive to temperature. Prolonged exposure to high temperatures can cause these components to degrade, leading to reduced performance and eventual failure. Thirdly, the breaker's lifespan may be shortened by high temperatures. The lifespan of a circuit breaker is typically specified in terms of the number of operations it can perform before it needs to be replaced. However, high temperatures can accelerate the aging process of the breaker's components, reducing its lifespan and increasing the risk of failure. To ensure the reliable and safe operation of circuit breakers, it is essential to select breakers with a temperature rating that is appropriate for the environment in which they will be installed. If the ambient temperature is expected to exceed the breaker's rating, several options are available. Firstly, use a circuit breaker with a higher temperature rating. Circuit breakers are available with temperature ratings ranging from 40°C to 70°C or higher. Select a breaker with a rating that is sufficient for the expected ambient temperature. Secondly, reduce the ambient temperature around the circuit breaker. This can be achieved by providing ventilation, installing air conditioning, or moving the circuit breaker to a cooler location. Thirdly, direct the circuit breaker. Dirty involves reducing the breaker's ampacity rating to compensate for the high ambient temperature. The NEC provides guidance on directing circuit breakers in Table 310.15. The ampacity of a conductor, as defined by the National Electrical Code, is the maximum current in amperes a conductor can carry continuously under the conditions of use without exceeding its temperature rating. This is a critical parameter for ensuring the safety and reliability of electrical systems. Several factors influence a conductor's ampacity, and it's important to understand these to select the right conductor for a given application. Firstly, the size of the conductor is the primary determinant of its ampacity. Larger conductors have a lower resistance to current flow, allowing them to carry more current without overheating. The cross-sectional area of the conductor directly relates to its ampacity. Secondly, the material of the conductor affects its ampacity. Copper and aluminum are the most common conductor materials, and copper has a higher ampacity than aluminum for the same size conductor. This is because copper has a lower resistance to current flow than aluminum. Thirdly, the insulation type of the conductor plays a significant role in its ampacity. Different insulation materials have different temperature ratings, which determine the maximum temperature the conductor can withstand without degrading the insulation. Conductors with higher temperature rated insulation can carry more current than those with lower temperature rated insulation. For example, THHN insulation has a high temperature rating than TW insulation. Fourthly, the ambient temperature surrounding the conductor affects its ampacity. High ambient temperatures reduce the conductor's ability to dissipate heat, which decreases its ampacity. The NEC provides correction factors to adjust the ampacity of conductors based on ambient temperature. Fifthly, the number of current-carrying conductors in a raceway or cable influences their ampacity. When multiple conductors are bundled together, they generate more heat than a single conductor. This heat reduces the ampacity of each conductor. The NEC provides adjustment factors to reduce the ampacity of conductors based on the number of current-carrying conductors in a raceway or cable. When selecting conductors for a specific application, it is essential to consider all of these factors to ensure that the conductors are adequately sized to carry the expected current without overheating. The NEC provides tables and guidelines to assist in selecting the appropriate conductor size and type for various applications. In addition to ampacity, other factors to consider when selecting conductors include voltage drop, mechanical strength, and environmental conditions. Voltage drop refers to the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can negatively impact the performance of electrical equipment. Mechanical strength is important for conductors that are subject to physical stress or vibration. Environmental conditions such as exposure to moisture, chemicals, or sunlight can also affect the performance and lifespan of conductors. The 4/0 copper THHN conductor mentioned earlier is a common choice for many electrical applications due to its high ampacity and versatile properties. The 4/0 designation refers to the American wire gauge or AUG size of the conductor. The larger the AWG number, the smaller the conductor. The THHN designation refers to the insulation type of the conductor. THHN stands for thermoplastic high heat resistant nylon coated. This type of insulation is commonly used in dry and damp locations and has a temperature rating of 90 degrees Celsius. The NEC specifies the ampacity of 4/0 copper THHN conductors in Table 310.16. The ampacity depends on the ambient temperature and the number of current-carrying conductors in the raceway or cable. In a typical installation, a 4/0 copper THHN conductor has an ampacity of 230 amps to 260 amps. However, it is important to consult the NEC and other applicable standards to determine the correct ampacity for the specific application. The selection of appropriate overcurrent protection for conductors is crucial to prevent damage from overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. The size of the overcurrent protection device must be carefully selected to match the ampacity of the conductor it is protecting. The NEC provides specific rules for selecting the appropriate size of overcurrent protection devices in Article 240. In general, the overcurrent protection device should not be larger than the ampacity of the conductor it is protecting. However, there are some exceptions to this rule, such as for motor circuits and for certain types of equipment. It is essential to consult the NEC and other applicable standards to ensure that the overcurrent protection is properly sized. In summary, the ampacity of a conductor is a critical parameter for ensuring the safety and reliability of electrical systems. Several factors influence a conductor's ampacity, including its size, material, insulation type, ambient temperature, and the number of current-carrying conductors in a raceway or cable. It is essential to consider all of these factors when selecting conductors for a specific application. The NEC provides tables and guidelines to assist in selecting the appropriate conductor size and type for various applications. The selection of appropriate overcurrent protection for conductors is also crucial to prevent damage from overloads and short circuits. Always consult the NEC and other applicable standards to ensure that the installation is safe and compliant.